us look at some properties of the different systems, and then let us analyze whether a system is linear or linear time invariant or a causal, whether it is stable. All those things let us discuss in this session with some examples. Okay, let us start with some notation which helps us in understanding this session far better. Okay, let us take a system. Let us say this is my system. Okay, let us denote x of t as my input system. This is what we are assuming. Instead of x of t, I can have z of t, y of t, whatever. So this is what I am assuming. X of t is my input system, and let us say y of t is my output of the system. Okay, that's what we have shown in the slide also. We are denoting x of t as the input and y of t as the output. Okay, now let us see three different types of outputs. For example, let us say at t is equal to t0 is my current state of observation. That means I want to observe the output or find out the output at t is equal to t0. That is, what is it I am interested in? I am interested in finding out what is y of t0. So this y of t0, where I am observing or measuring, I am observing this or measuring this at a certain time of instant called t0. That is why this is called as the current output. Okay, so this is my current. That is, it is also called as a present. Okay, so what is that I am measuring now is my present state or present output or current output. Now let us see. For us now, let us take this. This is my time axis, and this is t0 at which I am observing. All those things which happen below t0 or which happen before t0, that is this side, they are called as the past inputs or the response of the system for a past input. So this is a past. Okay. Similarly, for t greater than t0, all these cases here, we call this as the future. That means we have three types of inputs for which we have three types of output. One is the input when I give a t is equal to t0 is the current or the present input, for which I will get a output which is y of t0, which is again a current output. Similarly, when I talk about an input which was given earlier to what? For us the standard time is t0. So earlier to this is called as the past input, for which there would have been a past output. Okay. Similarly, if there is any input which is given after t0, that is after this current, there will be an input that is given. For that there will be an output which is y of t0 plus. That means we are moving away from this. That is called as the future output for a system whose input is also future. That means t is greater than t0. That means I can have a present that is here t is equal to t0. For t less than t0, this is becoming past, and for t greater than t0, this is my future. So now let us analyze the systems on this understanding. So this must be clear. Okay, x of t0 is the current input. Okay, x of t for t greater than t0 is the future input, and x of t for t less than t0 is the past input. So we have these three types of inputs which help us in analyzing any system in further discussions. So what we have indicated in this slide, we said y of t0 be the current output for a current input of x of t0. So x of t for t less than t0 is the past input, for which there will be a corresponding output would have been present. Similarly, x of t0 is the current input, and x of t for t greater than t0 is the future input. So based on these three, we will try to analyze what are the different systems available. First, let us talk about what is called as a linear system. A linear system is any system that obeys the properties of scaling, homogeneity, and superposition, that is additivity. So these two things must be present for a system to be called as linear. What is that? The first one is a scaling property. That means if the input is scaled by a certain factor, let us say alpha, the output also must be scaled by the same factor alpha. So this is called as a scaling factor. Similarly, the other property that must be satisfied is called as a superposition. That means additivity. If the input consists of two signals and the output summation of two signals, the output must also be the corresponding responses, addition of the corresponding inputs. So that means output is also a summation, as is the case of the input. So these two must be satisfied for a system to be a linear system. Now, if a system does not satisfy any one of these properties, then it is called as a non-linear system. So for a linear system testing, we should check whether the system is able to scale, and the system must be able to do superposition, that is additivity also. Let us just see a small block diagram on the board. Okay, let us take a system. Okay, let us now take a linear system. I am calling this as a linear system. Let us give an input to this. Let us say this is x of t, for which there is an y of t, which is the output. Now, we said for this system to be linear, there are two properties that have to satisfy. The one of them is what is called as the scaling property. Okay, scaling property. That means, let us say my x of t is scaled by a factor alpha. It means I take a system. Okay, well, let us not label this right away. So we will give a input which is scaled by a factor alpha, let us say. Okay, alpha is some numerical value. So we are scaling x of t by a certain factor alpha here. Now, if the output earlier was y of t for the system, isn't it? So the output is also scaled by a similar factor alpha, then the system is called as a linear system. This is one of the conditions. We are not yet sure, but at least one of the properties has been satisfied. What is the property? The property is when I scale the input, the output also got scaled by the certain factor. So this is called as the scaling property. The output is getting scaled by a factor similar to that of the input. So this is one property which we have been satisfying. Let us look at the second property. What was the second property? We said additivity or superposition property. So let us look at that. Let us put it here. Now what we will do here is, let us take the input as a summation of x1 of t plus x2 of t. Okay. For x1 of t, obviously the output is y1 of t and the output for x2 of t is y2 of t. Now when I pass this to a system, let us say I take a system like this, okay, and I have passed this x of t. What is x of t for us here? x1 of t plus x2 of t. Okay. Now the output will be y of t, and this is equal to y1 of t plus y2 of t. Then the system is linear system. That is, we are satisfying the property of superposition. What is it we are doing here? x1 of t has a corresponding output, that is y1 of t, and x2 of t has a corresponding output y2 of t. Now when I am sending this one by one, x1 of t is sent in addition to x2 of t, and the output also will be y1 of t in addition to y2 of t. So this is in fact the superposition which also is being satisfied. Now let us look at these two things in combination. So when a system satisfies both the scaling property, or also called as a homogeneity property, then it also satisfies superposition property, and also called as additive property. When these two are satisfied, then the system is linear. Other words, what we can do is, here we are adding two systems x1 and x2 of t. That means we are doing addition property. Similarly here, this also can have a scaling property included. That means I can have x1 of t scaled by a factor alpha x1 of t. Similarly, x2 of t can be scaled by a factor, let us say beta x2 of t. Then what will happen to the output? Here you see the scaling is also there, additive is also there. We are combining these two properties. Now the output will be, again this is the summation which is being applied. The output also will be scaled by a factor with a corresponding output, and this also will be same. So this is the how you decide a system is linear or a non-linear system. Now we have put some illustration here as already we have discussed on the board, but let us also look at this. For a system H to obey the scaling property, we have to show that H of k of f of t must be equal to k h of f of t. To show system H obeys the superposition property of linearity, then H of f1 of t plus f2 of t must be equal to H of f1 of t plus H of f2 of t. For us here, we have taken H of f1 or x1 of t as y1 of t, that is the corresponding output, where H happens to be the transfer function of the systems. So we have seen these two. So these two properties must be obeyed for a system to be, of course, linear. Now let us look at the system which is called as time invariant, or it is time variant. So we have to tell from a system, given its equation or some of its properties, whether it is time invariant or time variant. That means we have to find out whether the output is dependent on time or independent of time. So let us see this here. A time invariant system is one that does not depend on when it occurs. That means a time invariant system is one that does not depend on when it occurs. Even if I delay the signal input, the output also will be the same, but it will occur at the delayed input. Okay, so that's what is called as a time invariant system. The shape of the output does not change with the delay of the input. If the input is delayed, that means the output shape will not change. That means the input with the corresponding output remains same even if the input is delayed. That is why this is called as a time invariant system. Let us see this. For example, let us say I have a input like this and the corresponding output is, let us say, is a something like this is my corresponding output. Let us say this is my starting point 0, this is t, okay. So this is also t and this is 0. This is my input, that is my output. Let us say the input is delayed by a certain factor t naught, okay. So that means my input is starting at a point t is equal to t naught, then the corresponding output, we said the shape will not change. That means the output response remains same, but it will be delayed by the factor at which is equal to the time delay of the input. That means the output also will occur at t is equal to 0 and the shape must be same. So we try to put the same shape here. So this is better. When this happens, it is said that the system is time invariant. So this is called a time invariant system. Okay, let us see this. That is, for a system H where H of f of t is y of t, H is time invariant if for all values of t, H of f of t minus t is equal to y of t minus t. That means the function which is occurring at t is equal to t naught, that is the input, the output also will occur at t is equal to t naught. Okay. So whatever is the delay in the input, the output also will be a corresponding delay, and remember the shape of the output is not changing. That means there is no change in the response of the output just because of a delay in the input. Even if there is a delayed input, the output essentially remains same, but the response will be also delayed. That is the only thing. That is why this is called as a system which is time invariant. Now let us look at a time invariant system. Time invariant system can also be called or can be classified as linear time invariant systems also, provided the system which is time invariant satisfies the properties of linearity. So that type of systems are called as linear time invariant systems, otherwise famously known as LTI systems. Now let us look at a system which is called as a LTI memoryless system. Let us look at a system which is a linear time invariant and is called as a memoryless system. So what is a system which is memoryless? Let us see the definition here. A system is memoryless if its output y of t naught depends only on the input applied at the same instant t naught or x of t naught, and significantly it does not depend on x of t for t less than t naught and t greater than t naught. That means every memoryless system is causal. So what is causality? Causality is a system which the output depends on the past and the present inputs and does not depend on the future inputs. That means when you correlate this with the memoryless system is one where the output depends only on the present, does not depend on the past. So one of the conditions for causality is it depends on the present and also on the past. That is why every memoryless system is considered as a causal system, but not necessarily all causal systems are memoryless, because causal system also says the output depends on the past also. Okay, memoryless system. So what is a memoryless system? Memoryless system is y of t naught, which is purely dependent on the time at which the input is applied, that is t is equal to t0, that is x of t naught. So the input is applied x of t naught and the output is x of y of t naught for a input which is x of t naught. The output y of t naught is exclusively or is only dependent on x of t0. That is, my output is based only on the input applied at a certain instant of time. And here significantly, this y of t naught doesn't depend on what happened when t is less than t naught, or in other words, there is no way of remembering what happened earlier. That is why this is called as a memoryless system. Output is only dependent on present. The past is not recorded, the past is not known, or the past is having no influence on the present input. Such a system is called as a memoryless system. Okay, and significant one point we are making, we say that every memoryless system is causal in nature. So I'll just tell you the definition for causality. The definition of causality is a system which does not have any prediction of the future or which does not depend on the past. Okay, that means past independency is a memoryless system and future prediction is not there. So these two, if you satisfy, this system becomes a causal. In other words, a memoryless system is purely independent of the past. Okay, so that is why every memoryless system is a causal system in nature. Every memoryless system is causal. So let's just look at a linear system again, a little bit of detailed information. Linear system means that when input to a given system is scaled by a value, the output system is scaled by the same amount. Time invariant system basically has a property that a certain input will give always the same output with regard to when the input was applied to the system. So always whatever is the response, that will be the same in spite of delay in the input's timings. Okay. So here we look at how we model a time invariant system. Generally a system is modeled with a differential equations. So when I look at differential equation, I should be able to tell from the differential equation that this particular system is time invariant system. So how do I do that? Okay. So time invariant systems are modeled with constant coefficient equations. That means a constant coefficient differential equation means that the parameters of the system are not changing over time, and input now will give the same result as the same input later. That means the same input I am giving, even if I give now or I give it later, let us say after 5 seconds, still the output will remain the same. So this is indicated by a constant coefficient in your differential equations. So when a constant coefficient differential equation indicates that the system is time invariant system. Okay. So as I said earlier, certain systems can be both linear and time invariant. We call them as, referred to as linear time invariant systems. Okay. Now let us come to a very important factor called as a causal or a non-causal system. So what is a causality, or what is a system which classifies itself as a causal systems? Okay. And if system is not causal, we call it as a non-causal system. Okay. Now let us see at a causal system. A causal system is one that is non-anticipative, that is the output may depend on current and past inputs but not future inputs. Okay. A causal system is one that is non-anticipative, that is the output may depend on current and past inputs but not future inputs. Okay. That means a causal system, a system is causal system. We have seen three factors, isn't it? T is equal to T0, T greater than T0 and T less than T0. So these are three different. Okay. A system is causal when the output depends on both the current and the past and there is no prediction, that means output does not predict. Okay. So this is a causal system. Okay. Whereas a memoryless system we have seen is this only. This is my memoryless system. That means my system is memoryless if it has no effect of these two, whereas causal system is called causal, where it not only depends on the present but also past also has a certain influence on the system. This is a causal system. That is why if you look at this diagram, all memoryless systems are causal, but not necessarily all causal systems are memoryless. So one way it is true, the other way it is not true. So all memoryless systems must be causal system, and my causal system here can be memoryless if there is no dependency on this, but can also be beyond it. That means only memoryless systems, all memoryless systems in fact are all causal systems. So this is the most important point. Okay. And one more significant point which we are talking about here is we are saying that all real time systems must be causal, because the fact that we know what has happened in the past and what is happening now. So system in a real time will always have a feedback of what happened in the past and what has happened in the present. System can be built, and the system generally has no ability to predict what happens in the future, that is t greater than t naught. We do not know what is the type of signal that comes. That is why most or almost all real time systems are causal in nature. But there are certain cases. For example, in image processing, let us say I am doing an image processing here. To calculate an image, let us say I have, this is of my interest, these are all pixels, let us say there are certain pixels in which the image has been broken. To construct the image, this is my present, I should also know about the past, I should also know about the future for us to do some image processing. So this type of systems which not only depend on the past but also have to depend on the future are essentially not causal. So image processing, so the statement which you are making that all real time systems are causal is with a certain reservations, that is in certain cases like image processing where we do need a prediction of the future also. So that type of systems are essentially not causal even though they are real time. In other words, causality is a system if it does not depend on the future values of the input to determine the output. This means that the first input a system comes at time t is equal to t naught, the system should not give any output until that particular time. Okay. So this is very important point. What does this point say? If the first input a system comes at time t is equal to t naught, the system should not give any output until that time. So there cannot be any output, of course, where the input is not applied. That means the input is applied t is equal to t0 and the output should happen at t is equal to t0 only and not earlier to that. Okay. So that is why a system is said to be causal. And let us look at an example of a non-causal system. Would be one that sensed an input coming and gave an output before the input arrived. Okay. It sensed an input and thought the input is coming or arrived and it gives an output. A causal system is also characterized by an impulse response ht that is 0 for t less than 0. That means the impulse response h of t will be 0 when t is less than 0. This is how we classify a causal system. Let us move on. Let us find out about what is a stable system and how do we classify a stable system or an unstable system. Okay. What is a stable system? A stable system is one where the output does not diverge as long as the input does not diverge. Okay. So I give an input in a certain limit of values, then the output also will not go out of these values which we have given in the input. That means if there is no divergence in the input, the output is also non-divergent. That means a bounded input produces a bounded output. So such a system is called as a BIBO, bounded input, bounded output, stable. So it's called as bounded input, bounded output, stability. So here you look at an equation here. So what does the equation say? We have applied x of t and let y of t be the output of the system. Then the y of t is less than or equal to my, where my is less than infinity. Provided, what we say, the input must also be not divergent. This means the input values also must be bounded. So x of t again is bounded by a condition, that is x of t is less than or equal to m of x, where m of x is less than infinity. That means the values of the input and the values of the output are not going beyond infinity. That means they are not diverging. The condition here is that the input x of t is less than or equal to mx, which is less than or equal to infinity, then only the output y of t is less than or equal to my, which is less than infinity. That is why the system is said to be bounded input, bounded output, stable. Okay. So, any bounded input yields a bounded output, that is why we call it as a BIBO system. That means a bounded signal is any signal such that there exists a value, the absolute value of the signal is never greater than the sum value. Okay. As the value is arbitrary, at no point can the signal tend to infinity. So, we should ensure that the signal is not moving towards infinity, it is in fact having a certain value which is always less than infinity. So, this is the condition for BIBO stability. So, let us look at continuous time definition for BIBO stability. That means integration minus infinity plus infinity h of t dt must always be less than infinity. Okay. That means we say the transfer function is absolutely integrable. So, let us take this condition here. Let us take a continuous system. This is a continuous system. Let us say I have taking this transfer function h of t, and when I integrate this, then the integration must be less than infinity. In other words, the integral must be absolutely integrable. When the integration happens only, we say the system is stable. This is in the case of a continuous systems. So, of course, when you move to discrete time systems, what is it we have to do? An integration gets converted into summation. That means my summation must be also absolutely summable. In other words, if I take the summation here from minus infinity to plus infinity, okay, h of n, then this summation must be less than infinity. Okay. So, discrete time system, this is the condition. For the continuous time system, that is the condition for BIBO stability. So, looking at this equation, integral minus infinity plus infinity h of t dt is less than infinity. In other words, the transfer function is absolutely integrable. Now, when I move from continuous time to discrete time, then we make the standard transition from integration to what is called as a summation. Then h of n must be absolutely summable. That means when I add different values of h of n, they must always result in a summation which is less than infinity. In other words, if you look at the condition for discrete time BIBO stability, then it says summation minus infinity plus infinity mod h of n must always be less than infinity. So, this is the two conditions which we have to ensure to analyze whether the system is stable or system is not stable. If it is absolutely integrable oblique absolutely summable, then the system is stable. Otherwise, the system diverges and it is called as a unstable system. Okay. Now, we have seen two types of transformations. One is the Laplace transformations and the other one is a Z transforms. So, when I talk about a Laplace transform and what is a condition for stability, then there is one important point which we are making here now. So, easily infer from the pole 0 plot of a transfer function, pole 0 plot of a transfer function. The only condition necessary is the j omega axis in the region of the convergence. The j omega axis must be in the region of convergence. If this is not there in the region of convergence, what happens is the system is not stable. Okay, let us look at this pole 0 plot here. Now, let us take this is my j omega axis and this is my sigma axis. Okay, for systems to be stable, the pole 0 plot must be encompassing the j omega axis. The region of convergence must be there. For example, we have a pole here, okay, and this is my region of convergence. This is my region of convergence. Okay, in this region of convergence, you see the j omega axis existing. So, when these type of plot is given, the system is stable. Similarly, let us look at a system which here let us say this is my region of convergence. And where is the j omega axis? Is it present in the region of convergence? No. So, the j omega axis is here somewhere outside the region of convergence. So, this system is unstable, whereas this system is stable. So, the simple way of doing this is take a function convert into Laplace transform, plot the pole zeros, and from the pole zeros given, you can always identify whether the system is stable or unstable. This is with regard to stability versus the Laplace transformation of that. Necessary is the j omega axis is in the region of convergence, that is, it must be in the region of convergence, that is ROC. That is the case in the Laplace transformation. Similarly, let's look at stability and Z transforms. So, in discrete time signals in the Z domain, the ROC must contain the unit circle. If the ROC contains a unit circle, then the system converges and the system is stable. If the ROC does not contain the unit circle, then the system is unstable. This is in the case of a Z transform. So, the calculation of stability or the lack of it for a system is definitely very easy when I know its Laplace transform or its Z transforms in the case of a discrete time systems. Let us move on. Let us see some problems. Okay, we will try to find out if a system is causal or all other things which the question says. So, let us start with the first problem. What is the first problem saying? The first problem says, given an equation here, is the system causal? That is what is the question asked. Let us write this on the board. Let us see the problem 1 now. Okay, let us look at the problem 1. The problem 1 statement is as follows. Here we will again stick to the notations which we have made in the first slide. What is it we have said? We said that y of t is the output of a system and x of t is invariably the input of a system. That is what we have assumed. These variables can change depending upon type of material which you are referring to. But here, for us to maintain the uniformity, we have assumed that y of t is used for representing output of a system and x of t is used to represent the input of a system. So, what is y of t here? Y of t is the output of a system, particular system given to us, which is actually an integration of tau is equal to 0 to t plus 1 x of tau d tau. Now, we have to see the system is causal or not. That is what we have to assume. Now, if I look at this, let us see the dependency of y of t. If you look at this, the output response, this is the response, okay, is, okay, if you look at this, is dependent on x of t at t plus 1. T plus 1 is a prediction, you are going further away. Now, let us say a t is equal to 5 seconds and t plus 1 will become 6 seconds. That means future. We are going into a future. That means the output is dependent on the x of t for a future value of t plus 1. So, is the system a causal? No, because a causal system is not dependent on the future. So, that is why as y of t response is dependent on x of t or tau whatever at t plus 1, isn't it? This is the dependency of y of t on x of t or x of tau for a value t plus 1. Therefore, the system is, okay, we will write as here, as y of t response is dependent on x of t at t is equal to t plus 1, we say that system is not causal. System is absolutely and not a causal system because of the integration which is happening up to t plus 1. Had it been t, then this would have been a wonderful causal system. Okay, let us look at the second problem. Now, let us see the problem 2. Y of t is integration of tau is equal to 0 to t x of tau d tau. The significant difference between the earlier problem and this problem is, if you look at this, we are stopping at t, okay, that is the present. The system does not depend on future values. Therefore, what do you call this type of system? The system is called as a causal system. So, let us write down that y of t, for us y of t is what? The response, okay, or the output. So, this does not depend on future values. Okay, when I say future values of what? Of the input. So, because we are stopping at t, t is the present, isn't it? We are not going into the future. T plus anything is a future. So, we are stopping at t. So, this system does not depend on future values. So, what is the type of system? Therefore, the system is a causal system. So, we are able to just tell from the equation itself what is the causal system, what is a non-causal system. So, 1 and 2 are very good examples which actually put you in the right direction of analyzing a system with a given equation, whether a system is causal or it is a non-causal. Okay, we have seen the first two problems which were based on a continuous time system. Let us look at just let us move on and just look at a discrete time system. Okay, and the problem 3, we have to find out whether this discrete time system is causal or non-causal. If you look at this equation, then we can tell from the equation itself that this is causal or this is not causal. Let us analyze this, okay, step by step. Now, let us look at y of n. This is my current output, right? N is a current output. Okay, the current output is, first of all, this factor is dependent on a past. So, this is causal because dependency on past is also a causal system, whereas this is a current. So, this also is a causal system. So far so good, but when you come here, you see there is a future input that is involved. That means the system is not causal. Okay. So, first two terms actually in fact make your system look as if it is a causal system, but when you look at the third system is n plus 1, which is a non-causal system. So, let us just put in words, that is y of n is dependent on, okay, x of n plus 1, that is a future value. Okay. Therefore, the system is not causal, or you can say it is a non-causal systems. Let us also take this opportunity to find out whether it is a memoryless or a system which is having memory. Okay, if you look at this, there is a past that is being involved along with the present. So, this happens to be a system which is having a little bit of memory also. Let us look at problem 4. The problem 4 says y of n, that is the current output, depends on 3 of x of n minus 2 minus 0.5 x of n minus 1 and x of n. When you look at this equation, there are no future values that are indicate the dependency of y of t on the future values, that is there is no plus 1 term here anywhere. So, when you look at this, this is an indication that the system is a causal system, okay, because there is no future values here. So, this becomes a causal system. Let us look at problem number 5. Now, in this we have to find out whether the system is memoryless, time invariant or it is linear. So, all these three conditions we have to find out whether this equation is satisfying those. The system equation is satisfying this classification as it is, whether it is memoryless, whether it is time invariant or whether it is linear. Okay, let us talk about each one of them in separation. Okay, let us first talk about the system first. So, what is that? We have to find out whether the system is memoryless or with a memory. If you look at this, y of t here is dependent only on x of t. So, there is no dependency on the past values. So, this is a system which is memoryless. So, I will say this, y of t is memoryless, okay, because of this fact. Then let us see if there is any time invariance. Is this invariant with respect to time or there is a variancy with respect to time? If you look at this, the coefficient here is 1.5 is independent of t. That means it is time invariant. Okay, this is time invariant. Similarly, let us look at the third point, that is we have to classify whether this is linear or non-linear. Okay, we have to identify that. So, linearity, let us look at this first. Let us say let x of t be written as x1 of t plus x2 of t. So, what will be y of t will be equal to now? Y of t will be equal to 1.5 into x1 of t plus x2 of t whole square. So, this will be equal to 1.5 into x1 square of t plus x2 square of t plus 2 x1 of t x2 of t. Okay. Now, this is, there is y1 of t involved here plus y2 of t involved here plus an extra term, isn't it? So, this is the extra term we have. For a linearity property satisfied, what is it we have to show? We have to show the output is similar to input. What is the input here? x1 t plus x2 of t. So, part of it y1 to y2 t plus something extra is there to x1 of t x2 of t. So, system is not linear. So, I can write this as not linear. Okay, this is clear. Let's just summarize this quickly. Now, y of t is memoryless because the dependency of y of t is only on x of t. So, that is memoryless. Second, this is time invariant because 1.5 the coefficient is not having any term which is related to t. So, this is becoming time invariant. And linearity we have checked. What is the linearity? We have taken x of t, x1 of t plus x2 of t, and we have calculated y of t, and in fact we have proven that this is not equal to y1 of t plus y2 of t. The system is not linear. For a linear system to be considered as linear, two conditions must be satisfied. What are these? The first one is superposition, which we have seen. The other one is scaling. So, superposition has failed. So, there is no need for us to talk about scaling. That is why we have classified this as a not linear system. So, this is how we have decided a system properties based on the system response or the system output. Now, let us see the sixth problem. Sixth problem, again I have to see whether the system is memoryless, time invariant or linear. So, these three properties we have to see. Now, first of all, let us look at this. So, y of t is x of t dependent only on that. So, this is memoryless. Okay. So, this is done for us, right. Second is we want to find out whether it is time invariant or variant. In fact, this is time variant because of the presence of 2t here. There is a factor which is dependent on time. So, this is time variant. Okay. And we have to see whether it is linear or not. This is in fact a linear system because if we say x of t can be written as x1 of t plus x2 of t, then output y of t will be 2t plus 1 x1 of t plus 2t of 1 x2 of t. So, this is equal to y1 of t plus y2 of t. Okay, this is satisfied. So, the system is linear. Okay, we can say that clubbing all this together, this is an linear time variant memoryless system. Okay, LTV memoryless system. That is what is your question. So, this is simple. Look at the equation, look at the dependencies, then you can just put down what is the system type. Now, let us look at the problem 7. The problem says y of t is equal to cos omega ct x of t. Now, we have to say whether this is memoryless. Yes, of course, this is memoryless. Okay, this is memoryless. Okay, because of dependency of that. And then as you see here, this is a cos omega ct. So, this is time varying. So, we have a time varying. Then we have to see whether it is linear or non-linear. Then again for that, let us say x of t is equal to x1 of t plus x2 of t. So, what is y of t? Y of t will be cos omega ct, okay, x1 of t plus cos omega ct, cos omega ct, I repeat, cos omega ct x1 of t plus cos omega ct x2 of t. Okay. For this, what is the response? y1 of t. For this, what is the response? y2 of t. That means x is equal to x1 of t, x2 of t, y of t is equal to y1 of t plus y2 of t. So, the system is what? Linear. Okay, memoryless, time varying and linear. So, this is again LTV memoryless system. Okay. So, this is the 7th question. Let us see the problem number 8. So, what is given? This is a discrete time system, as you are aware. Y of n is 1.5 x of n whole square. Now, let us see again the same point here. There is no dependency, okay, on the past values. So, there is no memory involved. So, I call the system as a memoryless system. Wonderful. Then again, time varying or time invariant. Because of the absence of any t here, this is time invariant. Okay. So, this is system which is time invariant, and this is non-linear because of the square term involved, because we said when a square term is involved, we have x1 square plus x2 square plus 2x1 of x2. So, the 2x1 x2 is coming extra. So, that is not satisfying superposition principle. So, this is a non-linear system. So, this is a non-linear time invariant memoryless discrete system. Now, let us again analyze whether the system is a memory or memoryless system, is it time varying or time invariant, or whether it is a linear or a non-linear system. So, when you look at this, of course, this is memoryless again. Okay, so, this is a memoryless system and this is time varying because of the dependency on 2n plus 1, this is time varying, and finally, this is a linear system, okay, because it is simple x of n and not a and no square terms are involved. So, when you break up x of n into x1 of plus x1 of n plus x2 of n, similarly, I will get y of n which is equal to y1 of n plus y2 of n, of course, scaled by a factor 2n plus 1, that is always there. So, this is how a discrete system is. This is a linear time varying LTV memoryless system. Now, let us look at this 10th problem. This is a little practical problem to a real time system. Okay, let us see this. Consider a memoryless system whose input u and output y are related as shown in the figure below. Let us see that quickly. If the input u is known to limit to the immediate neighborhood of u not shown, develop a linear equation to describe the system. It is assumed that the slope of the curve at u naught is r. So, let us move on to the next slide. Okay. If you look at this figure x and y, you see this x axis and y axis, u and y naught, there is a slope of given r naught. That means, let us solve this problem. That means, let us put x bar of t. This is nothing but x of t minus the small change that is happening at u naught. So, we will put this here u naught. Similarly, let y naught, y bar of t will be y of t minus u naught. Okay. If these changes are very small in value, I can write y of t as r of x of t. Okay. This is the linear equation which we have developed. The system is, of course, linear. Linear because the slope given was r, and my assumption that the changes are not many. The changes are very small. So, I can have an equation y of t is r of x of t, or to encompass the whole thing, I can just put a x of t because of we are looking at around u naught. So, I can write y bar of t is equal to r of x bar of t. In fact, x bar of t is x of t minus u naught, and all those things we take in consideration. So, this is a approximate linear model. This can be practically developed.